Okay, so let me go on. One thing I should say, so because some people were asking me about this, if you want to know more about this, there's a nice review of this CFT approach of the combo effect, which is due to Ian Affleck. And so this is ContMat 95-12-099. So if you want to get more details about this, I really recommend this. Okay, but again, in that review, he doesn't do the full Kac-Moody story. He is more like an intuitive way, like I was doing here. But anyway, so do take a look. Okay, so the next thing is to tell you about large N. Before I go there, I have to introduce 3 more terms, which are the terms critical, over and under screening. And so this means, so in the simplest example, so our impurity spin was a half, and there was essentially one species of electrons, and then there is a singlet in the IR, because essentially just drawing this pictorial, you have one spin up and you have one spin down of the electrons, and then this nicely can form a singlet. Now, if we have different values of S and K, sometimes it's more complicated, but so there's something called critical screening. And so this happens when S is equal to 2K in generality, so then just, okay, it's a very stupid drawing. You just have enough spins of electrons to make up one singlet again. But then you can ask, well, what happens if I don't have enough or if I have too many, okay? And that's called over and under screening. So under screening, this is when K is less than sorry, did I write this correctly? Okay, let me write what I have written here. I'm a bit confused because I know I can't follow, but so when K is less than 2 S impurity, then the system has insufficient channels to screen the impurity completely. And so there is a residual spin, which is mod S minus 2K. And overscreening is the other case. Which is when K is bigger than, there's something that's wrong with this factor of 2. It's somehow, it doesn't match, but okay, let me check this for tomorrow. Let me just write down what I have here. I think it should be on the other side, but okay, never mind. The physical idea is that there's too many electrons to screen the spin, so then, so just very intuitive. And so essentially you have the spin in the middle, and then more and more electrons come there, and this leads to some complicated non-Fermi liquid behavior. Okay, so that was to complete these notions of the original Kondo model, and so now the next important thing which I want to show to you is the large n limit. And that's, of course, super vital if we want to do gauge-gravity duality. And so now this means we take a spin symmetry which is SUN with n going to infinity, and at the same time lambda goes to 0 with this number lambda times n being fixed. And so this can happen for any k. Although later, for our gauge-gravity model, we will restrict to the case where k is equal to 1 for simplicity, but you could do this for more k's. Okay, so first, let's look at this in QFT. And so this is a vector large n limit as compared to the matrix large n limit, which we usually have in gauge-gravity duality.
So can you repeat what is the particularity of the overscreen?
Okay, so it's just the, okay, so it's the, so the critical screening, you can make up a singlet. In the underscreen case, you don't have enough of these, and then there's a residual spin being left over. Overscreening means you have more electrons than just to make up this. So essentially some of them kind of form a singlet, but then all these others kind of join on top, and then you have a kind of onion structure where they all kind of group around this impurity, and this leads to some non-Fermi liquid behavior. So essentially, I mean, it's an unequilibrium situation where the electrons tend to form a singlet, but it's not possible.
But you can form the singlet in the SUN group, right? It's just not a singlet.
Yeah, okay, but
SUK, because there are too many flavors.
Yes, that's right. Yeah. So I mean.
So how does affect the physics of the?
No, I'm just saying. Okay, so you have more electrons than necessary to make up a singlet.
Okay.
And then so this entails some non-Fermi liquid behavior.
Okay.
This is the statement. Okay.
Thank you.
Sorry, is the 2 in the correct place?
Sorry,
Yeah.
where are you?
Yeah.
Okay.
Yeah, you have written S equal to 2k there.
Yeah, I was
K
saying.
equal to 2s.
Yeah. There's something wrong here. I think this factor is wrong. It should be on the other side. No.
Yeah, that's what.
Yeah, that's what I'm thinking too. While I was writing this. Sorry. Okay. Is that correct? No.
And okay, there again you have S minus 2k.
Sorry.
See, yeah, there again. I mean, somehow these are incompatible, right? You have written k greater than 2s, but there is s minus 2k.
Yeah, okay. So, you're completely right. I think let's leave it like this, and I will tell you tomorrow morning in 5 minutes I will get this right tonight, because if we start doing this now, sorry, there's some typos there. I will get this right by tomorrow. Okay. Okay, but let's continue with the large n limit. Okay, so in fact, if we consider this large n limit, so vector large n means so the number of degrees of freedom goes like n and not like n squared, as we will consider later. Okay, so then in this case you can actually do a saddle point approximation and solve the model maybe solved exactly in the saddle point approximation. And so then essentially we can learn everything about the model in this large n limit, and then of course we can look at 1 over n corrections. Okay, so, and in fact, okay, so we are heading towards having a gauge gravity dual. And so what I'm going to tell you is that how are we, so maybe you start thinking about how could we do such a thing in ADS-CFT? Well, I told you already we get this SUN from the spin symmetry, but then how do we get the screening effect in gauge gravity duality? And so the answer to this question is we are going to get a superconductor in 0 + 1 dimensions, which is possible in the large n limit. So normally you can't have phase transitions in less than 2 dimensions or in 2 dimensions. But here in the large n limit, this is no longer true. And so we will have an ADS2 holographic superconductor, if this means something to somebody. And in fact, what will happen is that a particular operator will condense, and this condensation will have the same effect as the screening. And this is only possible in the large n limit. Okay. Sorry?
The system is 1 + 1.
Yes, but the impurity is 0 + 1. So the dual of the impurity will be ADS2. But you're right, we will have an ADS3 space, and this has an ADS2 subspace. Like before, we have a 1 + 1 dimensional electron system, and we have a 0 + 1 dimensional impurity. So it all goes up by 1 dimension. So we have ADS2 inside ADS3. Very good. Okay, I will come to this later. Let me quickly explain. So we need this operator which condenses in this ADS2 space, and this we obtain in the following way. So, so for ADS-CFT, it is useful to consider a large n solution in which the Kondo effect appears as superconductivity. So superconductivity means we have a new ground state where a condensate forms in 0 + 1 dimensions. So, and this is possible only in the large n limit, of course. So n has to be strictly infinite, and so here we will have a phase transition, but then when we look at the 1 over n corrections, they will smoothen this into a crossover. Okay. Okay, so for doing this, we consider a totally anti-symmetric representation of SUN. Okay, so the Young tableau will be we have Q boxes in a row. Okay, so these are Q boxes. So this is totally antisymmetric, and Q has to be less than n. Okay, and now there's a super important trick in condensed matter physics which is the introduction of so-called abricos of pseudo-fermions, which just means we will write our spin in a bilinear of some fermionic operators. And that will precisely allow us to write down this superconducting model. So the next point is to write the spin. So this was SA was our spin in terms of so-called Abrikosov pseudo-fermions. And so these are called chi, and which transform in the fundamental of SUN. Okay, so this means we take our operator SA and write it as chi dagger. So I is again this index for the channels if we want to include them. And so this is a representation of SUN. So this totally antisymmetric one. So A goes from 1 to n squared minus 1. Okay. So okay, so essentially we write our spin operator in 0 plus 1 dimensions as this bilinear, and so these are these Abrikosov pseudo-fermions. Okay, so now of course, if we now consider those as totally normal dynamical fields, then somehow we have enlarged our Hilbert space. And that's not possible, so there must be a constraint which constrains these fields to remove some of these new dynamical freedom, degrees of freedom which we seem to add. So there has to be a constraint which has to be added. Okay, I'm trying to avoid to make it wet again, but I see this is so hard work. Okay, good. Okay. So there's also an extra symmetry because now we can phase rotate these things and these operators, and we still get the same result as before. So so there's an additional kind of spurious, so introduced by hand symmetry. And so we have to introduce a constraint. to remove any new or any additional degrees of freedom. And what we do is we take chi dagger chi is equal to Q. So Q was this number of boxes in your totally antisymmetric representation. And and we fix the charge density of these Abrikosa fermions to coincide with this Q, which then removes the additional degrees of freedom. And okay, so now the crucial thing is that we can form an operator involving one of the electrons and one of these Abrikosa fermions. And that will be the operator which condenses in our ADS2 superconductor later. But it can also condense just in a field theory model. So we now define a singlet. So this is an SUN singlet operator. And it's crucial that this SUN singlet if we want to do ADS CFT. And this operator is in 0 plus 1 dimension, so it only depends on T. And so this is defined to be psi dagger. So this were these left-moving electrons which we had, and we multiply this with one of this chi. So I'm sorry if you can't read it. Let me put a... So this is super important. So this new operator will be the key to the entire ADS CFT analysis. Okay, and now if you count the dimension of this operator, then you see that the dimension of this operator is actually a half. Okay, now we can rewrite our Kondo interaction in terms of this operator. So now we can use a so-called Fiat's identity. If we multiply these T representation matrices, so if we have we multiply this together, and then we get a half times delta alpha delta delta beta gamma minus 1 over n. So this is the trace term, alpha beta gamma delta. And of course, if n goes to infinity, this second term will no longer contribute. So, and okay, alpha, beta, and so on, they all go from 1 to n. Okay, and now using this, we can rewrite our interaction. Maybe I do have to take some water again. Sorry. So then using this, we find for the Kondo interaction so lambda delta of x j a s a, this was our interaction. And now if we do everything carefully, okay, so these are always left-handed. I shouldn't write, so I will drop these L's, but okay, so these are all left-handed fermions. And then here we have our Abrikosov. So okay, this is just the current J, and this is this spin current. Okay, so now who can tell me what the result of this calculation is? Okay, I take this product using this identity. Previously, I've drawn a red box around this operator, so somehow this must be important. Okay, so then now tell me what am I going to get?
Oh, that.
Yes, great. So, wonderful. So you're paying attention. So this is the leading term. And then there's a sub-leading term, but we can forget about it because n goes to infinity. So what is the technical name of this kind of operator? I mean, this is just an example, but so O is a singlet, and I multiply two singlets together. What is the name of such an operator? Yeah, it's a double trace operator, great. So, but, okay, this name is a bit strange because I didn't take any trace, but okay. Okay, so let me call this double trace in quotation mark operator. Because, so normally, for instance, if you do ADS-50 and all your fields are in the odd joint representation, then if you define some singlet operators, there always has to be a trace. Here now we work with all these fundamental fields, so we get a singlet by just multiplying a fundamental and an anti-fundamental. And okay, so but this object is gauge invariant by itself, and now I multiply two gauge invariant operators together. And by analogy, I call this a double trace operator, although I didn't take any trace. But we can use some standard techniques in ADS-CFT which will treat these double trace operators to analyze the RG flow triggered by this operator. So this is now our marginally relevant operator, which is going to trigger our RG flow from the UV to the IR. Okay. So okay, so and all of these operators will actually have gravity duals. So so I'm getting closer to talking about gauge gravity duality. The last final thing which I have to say is, what happens if we turn on this operator? Well, there will be a critical temperature below which a condensate of this one of these O's will form. Okay, so okay. So we have the following picture. So we start in the UV at our fixed point, and then we switch on this marginally relevant operator, which was lambda times J times S, which we now in the large N limit can rewrite as lambda times O dagger. And then this flow flows to an IR fixed point, and so this would be at high temperatures, and this is at low temperatures. And so the key point now I want to emphasize that here a condensate. So this you can really calculate in this saddle point approximation in field theory. And so this operator forms. and this is below a temperature. So there's a phase transition at a temperature Tc, and this is of the same order but a little smaller than Tk. So Tk was our Kondo temperature. So, so the exact relation between Tc and Tk may be calculated analytically, but it's slightly involved and involves some harmonic numbers and so on. So I'm not going to do it, but I mean, so it's not just a guess, this is the result of a calculation. Okay, so essentially, by going to low temperatures, at some point we go below a temperature Tc, which is slightly below this Kondo temperature Tk, and then we have a condensate of this operator, and this condensate of the operator is then, so the presence of this condensate, which, remember, was a condensate of an electron times one of these abricose slave fermions, so signals the screening. Okay, so as before, we see there is a kind of pair forming of 1 degree of freedom of this of the spin and of the electron. Okay, so this is the electron at the value of the defect, of course. And so this formation of this condensate then really shows that you have a screening as we were discussing before. Okay, so all of this can be done in quantum field theory in the large N limit, but now already it gives us a lot of hints if we want to construct a gravity dual, what we have to do. Yeah?
So the theory and theory is free, right?
Yes.
And the one in IR
Is strongly coupled.
but you seem to give a field theory realization, a free theory realization. I mean, because you shifted the current. So
Yes.
And in terms of that, J is the theory free.
Well, okay, so the thing is, you flow to a strongly coupled IR fixed point, which is strongly coupled. So the original coupling is large, so you cannot do any perturbation anymore in this original coupling. However, you can do conformal perturbation theory about this new fixed point in terms of the so-called leading irrelevant operators. So you can add an irrelevant operator to flow out of this IR fixed point again. So you can do, you have a strongly coupled fixed point, so you can't do perturbation theory in the original variables, but you can do perturbation theory in the variables at this fixed point. So, and that requires this rewriting in terms of these currents. So it's a duality, really. I mean, you have a UV and an IR realization. So the symmetry is the same, but the operators kind of look different.
You mean the duality between UV and IR?
Yeah, exactly. Yeah, so this is a duality which is there before I even start talking about gauge gravity duality. Everything I said so far has been established 30 years ago in condensed matter physics, a long time before anybody was talking about gauge gravity duality. Now I will turn to the...
Sorry, in which sense is it duality? How?
In which sense is it a duality? Because, okay, so I have two theories which are given by the same Hamiltonian, but the operator representations are different. So, I mean, the theories have different operator content, but they realize the same symmetries of the same Hamiltonian. So that I would call it duality. And it also is a strong weak coupling duality, because in the UV it's free and in the IR it's strongly coupled.
Sorry. This new temperature Tc, does it appear also in the simple model where you have only spin and low N?
No. This only appears in large N limit.
Okay.
Because if you don't have a large N limit, you can't have a phase transition in 2 and less dimensions. So this entire phase transition story is an entire large N business. So you can calculate 1 over N corrections, but then it becomes a crossover. And yeah, I mean, this is using the large N structure. of course, you know, you should be able to combine the Kac-Moody and the large N case. Okay, this should be possible. Okay, I haven't thought about this, but. Okay. Good. So now it's becoming clear which operators we want if we do a gauge gravity duality. All right, so let me move to the next part, which is writing the gauge gravity dual for this model. And essentially, we see already all the structures which we want to recover. Okay, so first of all, why would you like to write a gauge gravity model for this well-understood field theory model? Well, the reason there's a reason you would like to learn something about the working mechanisms of gauge gravity duality itself. So if we can find a gravity dual of such a simple model, maybe we can also understand more about the gravity dual. But then the second thing is that also within condensed matter physics, although this model seems extremely well studied, there are still lots of unsolved questions. The most prominent one is if you take more than one impurity and form a so-called Kondo lattice. This is one of the big unsolved problems in condensed matter physics. I can't say anything about that yet, but there's some chance that by generalizing what I'm saying here, you can also do this for more impurities, and that would be very interesting. Then there's also questions like entanglement, entropy, quantum quenches, and how exactly this Kondo cloud the screening cloud forms in a real material. These are all unsolved questions also in condensed matter physics. So the motivation for doing this in gauge gravity duality is actually twofold. So one is you want to use this known structure to learn something about gravity duals in general, and second, you want to use this to study more examples of the Kondo model in condensed matter physics itself. Or more features, I shouldn't say examples, more features of condensed matter physics in this context. All right, so this as a motivation. Okay, so the first thing is I'm going to remind you of the ADS-CFT correspondence in about 30 seconds. Okay, I'm going to tell you about the most important feature, which will be super relevant here for writing a gravity dual for this model which we are considering. So as you know or remember, or maybe have heard, the best understood example of ADS-CFT is when you consider these three branes in type 2b supergravity. Okay, so this brings me to the gauge gravity duality. So the best understood example so this is Melasena 1997. So this is D3 branes, so N D3 branes in type 2b. Well, you start with string theory and then take a particular limit. So let me very quickly remind you of this. So we consider a stack of n D3 branes. And so within string theory, there's a duality there between an open string and a closed string picture. So this is my stack of D3 branes. And I can consider open strings which are attached to the stack. And this is dual to this closed string picture, where I consider these to be solitonic solutions in supergravity, which deform the space around them, and then my excitations are closed strings. And we have a duality between these. And then there's this important limit which is taken So first of all, when you take the string coupling to go to 0, which you should do to get a classical string theory, which is tractable, then this actually implies that n has to go to infinity, because essentially gs goes like 1 over n. So this is in this open string, and this is in this closed string picture. And then the second point is that this so-called Tuft coupling, which also is called lambda, and now we shouldn't confuse this with our Kondo coupling. So this is really the Tuft coupling, which is given by G Young-Mills squared times n. So this will become, this is a second step in this duality. If this becomes very large, then this means that alpha prime, the string length or the inverse string tension goes to 0. So there's a two-step limit which is involved. And once we take this limit, then in this limit here we get nx to 4 SUN super Young-Mills theory in 3+1 dimension with n and lambda large. And in the same limit here on the side, we get type to be supergravity on ADS 5 times S5. Good. So this is all nice, but now we want to get a gravity dual for the Kondo model. So what do we have to do? Well, okay, so let's look at the fields which are introduced and which we would like to recover now here. So what do we want? Now we would like electrons in the fundamental representation of SUN. In 1+1 dimensions. Okay, and then what we also want, we want abricos of pseudo-fermions. And these should be in 0+1 dimensions. Okay, so clearly this means we have to add something to this original picture with these three branes. And the simplest thing, or the first step which you can do, is to use so-called probranes. So, which you embed into this ADS5 times this 5 space, but you neglect their back reaction. So, probranes means neglect the back reaction on this ADS5 times this 5 geometry. Okay, and then to obtain precisely these 1+1 and 0+1 dimensional fermions, what you have to do is to add the 7 and the 5 branes. So to obtain this goal, so what we have to do is to add D7 and D5 branes as follows. So let's write all the dimensions. So 0 is the time direction, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is our dimensions. And so our n d3s, they are in these 4 dimensions. Now, to get the d7 branes, so in principle we can take an f of them. Later we'll make our life simple and just take one d7 brane. So now to get these chiral fermions in 1 + 1 dimensions, we will put them as follows: in the 0 and 1 direction, and then in the 4, 5, 6, 7, 8, and 9. So if you are familiar with string theory, this is actually a supersymmetry preserving embedding, and the strings between these D3 and the D7 branes, they will give you precisely this chiral fermions which we want. So this will give, so I should write this. Okay, I'm looking at the time. Okay, give me 5 minutes because I want to write down the duality and then I can take it from there tomorrow morning. It will take about 5 minutes. Okay, so the D3, D7 strings, these give us our chiral electrons. And then we can also put D5 branes. And these will actually give us the impurities. So they will be here in the time directions, and then we put everything into these internal directions here. Like this. So if we didn't have the D7 branes, this would actually also preserve supersymmetry. But then if you look at these D7 and the D5 together, you see that this actually has 2 ND directions only. And so this will actually be an unstable embedding if we have both of them. But okay, if you ignore for one moment these D7 branes, then these D5 branes will precisely give us these abricosal fermions. Okay, and then, okay, so the instability comes from the D7 and the D5 branes, and so this is an unstable model. But this is what we want because we want a superconductor. So this gives a tachyon, and so which then causes the condensation which we are after. Okay. And so essentially that tells us what our gravity dual model is going to look like. So we have a background which again is AdS5 times S5. And then in this background we will have D7 probes which wrap AdS3 times S5, according to this table, and the D5 probes which wrap AdS2. And here you can see our AdS3 and AdS2, which we really need for our model, times S4. Okay, and then I can also write a field operator dictionary for operators which are in the same representation of all the symmetries. So this is the last thing I want to do for today. And so let me get my field operator dictionary. Sorry. Yeah, okay. So here we have the QFT side, and here we have the gravity side. And so here we have our electron current. Which is in 1 + 1 dimension. And so this current, I've written it a couple of times. Now let me also write the space-time indices, not just the spin indices. So on the gravity side, this will be dual to a gauge field in ADS3. And actually, as I will explain tomorrow, it's a Chern-Simons gauge field, which doesn't propagate. Then we'll have the charge density for these Abrikoso fermions. And so this was chi dagger chi. And this will be dual to, so remember that this was equal to some charge density. And a charge density we get from a time component of a gauge field on the gravity side. But these fields only live in 0 + 1 dimensions, so this will be a Young-Mills field in ADS2. Okay. And then finally, we have this tachyon, which is a complex scalar. And sorry, no, I wrote it on the wrong side. And this is, of course, on the gravity side. So here we have phi, which is a complex scalar. So now, please show me that you paid attention today and tell me what I have to write on this side. So what is this complex scalar going to be dual to in our field theory?
The operator O condenses.
Yes. So the operator O, which condenses. So this will be dual to this. So, and the operator O, which condenses. Thank you. So this was psi dagger chi. So this is our singlet out of an electron in the slave fermion, and this will be dual to this complex scalar field. So this is also in ADS2, of course, because these chi's, they only live in 0 + 1 dimension. Okay, so essentially this already tells us what our ADS CFT model is going to be, but as you will see tomorrow, of course, the total model, which I have written down with all these brains, and this will be far too complicated to solve, especially because we don't know the potential for this tachyon. So at this moment, what we are going to do is to say, okay, this is all beautiful. Let's take this as a motivation for write a much simpler model, which contains the essential features of all this discussion, but which we can actually solve, where we can actually write down the equations of motion, solve them, and draw some conclusion for the physics. And that's what I'm going to do tomorrow. Are there any questions? So, thanks. Everybody's exhausted.
If not, then we can continue with questions and discussions at 5 o'clock. And we thank Johanna again for the very nice lecture.
Thanks.